In this video, I'll introduce covariance and correlation. So in a nutshell, correlation measures the strength of a linear relationship between random variables. So we keep talking about random variables as being independent. They're not always independent. There's sometimes relationships between these. For example, height and weight are not independent random variables for the same person. So before the mathematical definition, I'll tell you just the general heuristic or the general idea before. So here we have variables x and y as labeled by these axes, and there appears to not be that much of a relationship between them. And in fact, they're not. I randomly generated, there is no relationship. If we were to draw a line through these points that fits best, it would be about like this. So it would be about flat. So these variables are uncorrelated. X and y uncorrelated. And that happens when the line is flat. Here's another picture of different points, x and y. So in this case, in this picture, the points in x, low points in x correspond to low points in y over here. Similarly, high points in x correspond to high points in y. So as x gets bigger, y tends to get bigger. So if we were to draw a line approximately through all these points, the line would look about like this, and it would have positive slopes. So these are positively correlated. So here's another picture. In this case, when the x values are low, over here on the left-hand side, we see that the y values are high. And when the x values are high, the y values are relatively low on the right-hand side. That's what we're seeing inside this plot. So if we were to draw the line that best fits through these points, and they are approximately laying on some line, you might draw a line like this. This line is sloping down, so this is negatively correlated. That is, the variables x and y are negatively correlated here. So we have uncorrelated, positively correlated, and negatively correlated. All right, here we see in this picture another relationship between x and y. So this doesn't look like a line. On the left-hand side, it's sloping down, and then on the right-hand side, it's sloping up. So in fact, the way I draw this line is the way I generated the data using a quadratic function. So y is just equal to x squared, approximately, plus some noise. Okay, so that's what's happening. If we fit the best fit line through all these points, we might end up with something like this. It's flat. So it seems like they're uncorrelated. But in fact, well, I mean, they are uncorrelated, right? So the measure of uncorrelated, the meaning of uncorrelated is the linear relationship. So we draw this best line that we can, and it might well be flat, but it's important to understand that uncorrelated does not mean that x and y are independent or even unrelated. So they could be very much related to each other. One is a function of another. It just could happen that they have little to no linear relationship. So that's the only thing that correlation and covariance are measuring, is the linear relationship between variables. And now I'll give the definitions. So recall that the definition for the sample variance, the variance of x, if we have a bunch of observations, n observations, then we take 1 over n minus 1 times the sum of xi minus x bar. So it's the average squared difference from the mean is what the variance is. The covariance is pretty much the same thing. We take this same sum, and instead of squaring this, we have xi minus x bar. So we're looking at how xi differs from its mean and how yi also differs from its mean. So we can build the correlation using the variance and the covariance. So it looks as follows. We use R to denote the sample correlation. I'm following the book. So you can write it as the covariance of x and y divided by the standard deviation, or the square root of the variance of x, times the square root of the variance of y. So we prefer things like correlation and standard deviation over variance and covariance in the sense that they're more interpretable. That is, they're in the original units, and in the case of correlation, it is unitless. So it has no units at all, but this allows us to interpret it in terms of being units squared or units multiplied by each other. Here is another way to write it, just doing some algebra on it, but this is probably the easiest way to compute it if you're going to compute it by hand, given a bunch of numbers. So you just plug in your pairs of xi and yi, and you compute the mean of x and the mean of y, and use that throughout the equation, and then you can get the correlation coefficient. Or if you're really lazy, you can just plug all this into all R, and you can, for example, call the function cor of x and y. And that will do all this for you.